So last time we spoke about these two models, the spring model and the imaginary spring model, and the viscous damping model versus. And we said that in this model, the lost energy, U, let's say L, is proportional to the displacement, delta, D. And in this model, the lost energy is proportional to the velocity. So which is actually true? And to discover this, I'm going to ask you to go through this little bit of a thought experiment. So we're going to have a nice thought experiment to determine which one of these is correct. So say you have a piezoelectric material, and I slowly pull on it, very slowly, let's say over 5 minutes. I slowly increase the force. So here time equals 0, here time equals 5 minutes. The energy stored, and here's a stress, and here's a strain. So obviously this is the energy stored, correct? So 5 minutes. If we were to be using the viscous damping model, if we use the viscous damping model, what's the velocity here actually? Velocity is almost 0 because we're going so slow. Does that mean we have 0 losses? That this spring that we are stretching out, this piezoelectric material, which is kind of like a spring, right? The spring which is stretching out, does it actually, does no losses occur if we just use it at a really slow rate? Experimentally, this is false. This idea is not true. It doesn't happen like that. You actually lose energy. Proportional. The energy lost in the system experimentally now. This is not necessarily just scientific understanding. This is what we actually measure, that this energy that we are storing, you lose a certain portion of that energy. And you lose a certain portion of energy relative to the displacement. Not velocity. So it's appropriate to use complex representations, because complex representations help us to understand the material properties proportional to the stored energy. Use complex representations. So we're going to use a complex representation because it doesn't depend on velocity. It doesn't matter how fast you're driving it, driving the piezoelectric element. It doesn't depend. It depends on how far is it stretching. That is going to determine the losses. However, if you're only talking about a small range, let's take this graph again. Remember, I told you to show you this graph, and I showed you that. And I said that this is the resonance frequency. If you only want to predict the losses in a certain area for a limited frequency range, this is okay. Using this model, this mass spring damper system, although I said it doesn't work, it's okay. And why? Because look, velocity equals the omega times d, right? Let's say we're using this device, or we have a piezoelectric, material or whatever. Let's say we're only using it at the resonance frequency, plus or minus, let's say 1%. Okay, and so basically the velocity relation is only going to be plus or minus 1% of the displacement. varying obviously with this term. Therefore, since the velocity doesn't really have too much disparity with the displacement with regards to loss, if you end up calculating, and you can end up calculating an equivalent C, damping factor for this material system. I may post a different article on that, but if you end up doing a different, if you end up using this system, then it'll still work out. You won't get crazy off data. You'll get something which is reasonable. But however, if you want to apply this to a broad frequency range, which is often important for modeling and matching experimental data to impedance data, you'll need to use the complex representation. Because the losses actually depend on the energy stored. Similarly, we would use dielectric displacement. Dielectric displacement has a complex form because the energy lost in the electrical system is proportional to the energy stored. Proportional to the energy stored in that electrical system. And what is that ratio? E double prime over E prime equals tangent delta equals U energy lost, U stored energy. Actually, I'll show you something funny. The funny thing is that if you wanted to use this, you can actually represent this system in an imaginary form. How do you do that? It's kind of funny. Basically, you say the mass is imaginary. It's kind of a funny idea to think about. You see the imaginary, the spring is just normal. This exactly equals this case. These are equal. Where the mass is imaginary. And obviously that's nonsense, and nobody thinks that the mass is actually losing energy. There's no loss mechanism, no way to lose energy in a mass. Therefore, we kind of use this discrete component. And this is why we kind of like these systems. For a resonant system in a circuit, we use LCR, LCR, RCL, whatever. But we use this system, and in this system, it's the same thing. Okay, look, this resistor is proportional. Is representing the energy lost, and it's proportional to the current, not voltage. And we know that in actual systems, meaning in actual materials, not necessarily devices, and devices have a little bit, for example, a resistor, actually the loss is proportional to the current squared, but the power rather. For materials like capacitors, their loss is proportional to the stored energy. Therefore, it would be more appropriate if you're modeling some type of resonant system with the capacitor, you would use a complex value for the capacitance. This would be the stored energy. So I believe I kind of went over why we are using a complex form. So why the question you should be able to answer at the end of this video is, why do we use complex representations of parameters? And I'm going to tell you the reason is because complex representations of parameters allows us to model loss according to the stored energy. Loss is proportional to the according to stored energy. Kinetic energy itself is not intrinsically a lossy type of energy. It's a word. It's not a lossy energy. It doesn't have any loss mechanism but know that unloading and loading a spring, basically what you're doing is when you're converting mechanical to elastic energy, sometimes the mass is going really fast, and then when the mass starts going slow, you're actually storing a lot of energy, because basically the movement back and forth, if you know that you're moving back and forth, and sometimes the elastic energy is maximum, sometimes the kinetic energy is maximum, but basically that it's not the exchange of It's really the exchange of energy which is happening, the change in energy which is happening within the spring which is causing the losses, not not the fact that you're actually getting kinetic energy. That is not included in the losses. And this is why this representation, the mass spring damper, the damper, viscous damper, is inherently problematic to use in a viscous damper system for a piezoelectric material or any other material actually. But in some cases, that the mass spring damper does actually relate to reality. There's some certain cases of that, and this viscosity type of thing, obviously you understand it's viscous, so viscous fluids show this damper quality quite well. The faster you pull on it, the more it kind of pulls back at you. And so it's very good for liquids, and sometimes liquid system, maybe a resident hydraulic system, it's great. But for a piezoelectric material system, by which the lost energy is proportional to the stored energy, that in that case you definitely don't want to use a mass spring damper. You want to use complex. The other thing I want to say is so the first thing you should have learned from this is why do we use complex representation of parameters? The reason is because of the stored energy. The lost energy is proportional to the stored energy. And the other reason why we can understand why this mass spring damper is not appropriate for a piezoelectric material is if you look at the form of the zeta, and zeta is practically a damping constant. And zeta is actually equal to C over M over 1 divided by 2 times the resonance frequency, which is going to be M over K, 1 over the resonance frequency. So we see here that the damping coefficient depends on the C, which we expect, but also depends on the resonance frequency here. But for the other case, the effective damping parameter is just equal to this ratio, the ratio between the imaginary part, actually it's a real part over the imaginary part. I believe there's a 2 factor in here, I can't remember at this time, but basically it's proportional to this factor. So here we have all these material properties which don't belong here. They don't, we're comparing energies, we're not comparing real material properties, but these real material properties such as mass and the real stiffness is actually affecting the damping, which is not, it doesn't make sense actually. So we like this complex form. Actually, the complex form is pretty simple to solve. Actually, the mass spring damper system, the reason we use it is because we can physically see a discrete component. Okay, here's the damping, here's the energy, here's the kinetic energy, here's its elastic stiffness. That's the reason we use it, because it's simple to understand and see and kind of feel. But complex, it seems like weird. What is imaginary? What is this term? Why do we use this to represent real parameters? The reason we use it is because it works well, and it matches the actual data. So I've also, I don't think I've mentioned it, I have attachment on this page. If you go to learnpiezo.org, and you go to the lecture 6, which you're watching lecture 6, and you go to the attachment, you'll find one of the attachments says something like imaginary on it. And this basically, this document is going to basically walk through a case of a mass spring damper, but the damper is not a damper, it's a complex spring, and how that relates to the mechanical quality factor, if you are interested in this kind of a response. But it kind of develops this. I haven't really found something like this in another place in the literature. I'm sure it's been done, but I just haven't located it. But this is kind of a nice way. You've already understood the mass spring damper system, but how about the mass spring complex spring system? That's also important to understand from a mathematical perspective, and how do you solve that, and how does it all work out in the end. So thanks for watching. I hope I clarified this issue. And I think next time we're actually going to be solving a system, a piezoelectric system, but we'll simplify it to a mass spring system. Thanks for watching.